Thank you, everyone. Welcome to today's Microsoft Reactor session on pollen detection and biodiversity. A few housekeeping notes before we begin is that this session is being recorded and will be shared on our YouTube channel within 48 hours. I'll put the link in the chat as well. Live captions are also on if you need them. You can turn them on or toggle them on or off using the 3 dots in the tools banner on top. So if you need them, they're on. You can translate them to your preferred language as well. But the most important thing that I'd like to mention is that if you could, please check into today's live stream using the link that's on the screen. It's aka.ms/reactor-check-in, and it'll ask you and prompt you for a code. That's 13814. What really helps when you check in is that all the links or content that our speakers today will be sharing will be available on that check-in page. So if you check in, you'll get all the links. You don't have to copy them down from the slides or anything like that. So it just really helps you out. Lastly, I would just like to mention, please adhere to our code of conduct for today's session. Basically just means that we want to empower every person to do more, which means to do that, we don't tolerate any behavior that's harassing or degrading. You just be aware, be friendly, respectful, open to all questions, understanding of differences, and just be kind. So pretty straightforward, nothing too outside the norm there. Our presenters today will be taking questions up at the end of the workshop. So if you have them throughout the workshop at any time, just drop them in the chat. James will be monitoring that as well, so we'll definitely take everything up. And without further ado, I'll give it up to our speakers.
Thank you, Eamon. So I will share my screen just to have a few slides and talk about, just let me, can you confirm you see my screen?
Yes.
Perfect. So we are here to speak about a project that we have done about one year ago about biodiversity, about green tech, about AI, and about bees, and we will explain that with Jonathan and Kim. Just before we start, I just want to introduce myself. So I'm Jean-Pierre, call me JP. I lead innovation at Avanade France. I'm also a Microsoft MVP, working with the French community around data, but my passion is about innovation, so IoT, AI, and data, and it's the perfect mix to discuss about that project. And the guy behind the project, the technician, the specialist is Jonathan. Can you introduce yourself?
Hello everyone, I'm Jonathan. I work with GP since almost 2 years now. Before that, I was student at the Microsoft AI School in Paris. It's a program of 18 months to learn data science and machine learning. And now I'm data scientist at Avanade. And daily, I work on AI projects for customers or as part of internal innovation projects. So I'm very happy to be here with you this afternoon.
Thank you, Jonathan. And we both work at Avanade, but I will just take a small word about Avanade in a few minutes. But just before to introduce Kim, which is the customer, the guy with the idea behind, I just want to introduce Enric Lopez. He cannot be with us today, but he's leading artificial intelligence for Microsoft in France. And he initiate a program 3 years ago called Share AI. And thanks to that program, we mix competencies, skills from Microsoft people and partners like Jonathan, me, or other Microsoft employees, and social entrepreneurs like Kim that have projects for good. And the idea is to put some AI into that project, but sometimes it's not just AI, it's technology, and we are here to help. And I'm very proud that with Avanade, our company, and also Accenture and their foundation, we have the pleasure to help projects for the second year. So we are starting the third year offshore AI, and it's the second year for Avanade and Accenture, and we are very proud of that. Now it's time to discuss about green, about biodiversity, about bees, and the best people, the best person to do that is Kim, because he's at the beginning of the project. So I'll let you present yourself, Kim.
Thank you very much, Jean-Pierre. Then I'm Kim Nguyen. I'm a scientist. I work doing more than 20 years maybe on the honeybee colony losses in a university here in Belgium. But if I'm here today, it's also because I'm the CEO of BeoDiversity. And BeoDiversity is a social enterprise. We have founded BeoDiversity in 2012. And what's interesting is as we are social entrepreneurs. Our mission is really to regenerate the biodiversity, to reduce the pollution, but in the same time to create value for our clients, but also for all the stakeholders. In fact, we are really convinced in biodiversity in our team that we can create value and in the same time preserve the biodiversity rather than to destroy the biodiversity and our environment. Actually, we are working in 12 countries, and not really 9, but 12 countries now, actually including in US, where we are improving the environment. We are working with farmers, just to reduce the use of pesticides. We're working with industrial companies to reduce the use of the pollutants in the environment, and we are working with citizens, cities, and municipalities to improve the biodiversity. Though the reality is that to improve the environment, you need measurement to identify the problems. That's why we developed the BeeOMonitoring. It's a tool. It's a nature-based innovation to monitor the environment in collaboration with the honeybees. Yes, I said the honeybees. You can see all around me, my friends, as the honeybees. And the concept is that bees can act as natural drones. I worked to save the bees during many years, and now I'm collaborating with the bees to save the environment. Then I said bees can act as natural drones. In fact, just because in one beehive, we have 50,000 bees, and they will collect more than 4 billion of samples per year, all around their beehives to feed themselves. And it's in a radius of 1.5 kilometers. No other tools can collect so much samples. Then they will collect water, they will collect nectar, but they will also collect pollen. Then we have developed a device to collect the pollen on a daily basis to really monitor the quality of the environment. Why we're using pollen? Just because the pollen can fix all the pollutants that come from the environment. It's also because the pollen contains the DNA of each species of plant in the environment. That means that when we analyze the pollen in our laboratories, then we can identify more than 500 pesticides in the environment. We are looking for more than 20 heavy metals, but also we can evaluate the quality of the biodiversity in the environment. Actually, the problem is that we are working in laboratories. That means it's very time consuming and difficult to scale. That's a real issue for us, because what we want, in fact, we want really to improve the biodiversity and improve the quality of our environment everywhere, all around the world. But just for the biodiversity, we need in our laboratory to take each grain of pollen and to identify each grain of pollen one by one by microscopy. That it's a hard work. It's really hard to scale. And but what we wish is to improve our impact for the next generation. It is why we thought that the artificial intelligence can really help us to identify the origin of the pollen, to identify the pollen, and to measure the biodiversity. Then, just to finish, and finally, thanks to Avanade, thanks to Microsoft, and specifically then thanks to the program Share AI, actually we are working on it. Then thank you very much to them, and I will let them more explain in detail the technical aspect of what we developed together. Thank you very much.
Yes, thank you, Kim. So it's the purpose of the program to make that project meet people like Jonathan and me, because we are geek. And when Kim explained that bees are like natural drones, as a geek, I was very enthusiastic. So I said we need to help them, because there's some IoT, there's some artificial intelligence, but there's a lot of data. So okay, we want to work and to think about that challenge. So the idea is to use IoT to reduce the time to results. So the final purpose is to have some laboratory analysis of the pollens or the pesticides, and it takes time to collect from the hive, to put to bring to a laboratory, and then make some operations to identify pollens and to say that it's what kind of plant or flowers. So the idea was, hey, we are doing some IoT, and with John we have specialized on IoT and edge computing. So the idea was to make a device inside the hive to perform all the analysis directly in the hive, and to, for example, by connectivity, by 5G or whatever, send the result to BeoDiversity. But there's two challenges to do that. The first is we need some optical engineering, because to see a pollen, it's very, some pollens are visible with your eye, but most of the pollen are very small. So you need a microscope technique to make a zoom by 100 or by 200 to have something visible for an algorithm, an artificial intelligence algorithm. So it's the first challenge. And the second one is, once you see it, we discuss a lot with Kim and all the guys working in the laboratory. Once you can see the pollen, you can identify and count the pollens. And with that, these two information, you can make some assumption or some analysis about the biodiversity. So we decided to say that if you can see it, a computer can do the same. And we decided to develop an artificial intelligence algorithm that can identify the pollen on the image inside the hive. But it was too difficult. So we decided to focus only on the artificial intelligence part, because there's a lot of constraint with the optical engineering, because you have the focus, you have the light, you have also, I think, a microscope. It's something that is very expensive. So it's not suitable to have everything in the hive. But discussing with Kim, we conclude that we can help even with just one algorithm, because in the laboratory there's mechanism to grab the image of the pollens on the microscope. So the idea is to have a kind of automated microscope that just take the pictures, and then the algorithm can just save a lot of time to laboratory technicians. And it was precious. So we decided to work only on that algorithm. So it used deep learning. So it's we call that computer vision, but there's another a category called object detection. But Jonathan will explain that more precisely. So we decided to implement an object detection algorithm specialized to detect, to identify, to classify the pollens, and to count them, because if you can identify and classify each pollen, you can just make a density score of each one. And the first thing we have we need to implement that object detection algorithm is a training data set. So the first thing was to have that library, that data set with a lot of labeled pollen image. And here comes the problems for data scientists like John, and I will give you the mic.
Yes, thank you, Jean-Pierre, GP. Yes, indeed, the first thing to do is actually collect data, enough data to train an AI model. Potentially, you need millions of images. To do this, we add different sources, the samples provided by BeoDiversity, several palynology institutes interested in the project and wishing to provide their own samples, and some datasets available in open source on the internet, such as the OREM dataset, which provides thousands of images of pollen from many varieties of plants. But despite this, we had a real problem. We did not find enough different examples of what can be seen under a microscope, you know, the microscope cover slips. Indeed, we wanted to use object detection, and this computer vision technique requires examples of several objects on a single picture. And basically, we needed examples of what Kim can see daily through his microscope. I mean, thousands of examples of what Kim sees through his microscope to train our AI model. And we didn't have enough images. We collected only hundreds of examples. So we had the idea, the brilliant idea, to create new images ourselves from the images we already had. The principle is to cut out the pollens and the images and to arrange them randomly and on a brand new image. So the idea is to flip, to rotate, to play with the noise like traditional data augmentation, but going further, we developed a software to make this data generation. And we called it the recompositron, in French, with my French accent, recompositron. Its operation consists of automatically labeling the images to train the object detection model. So the objects, the pollens, are randomly dispatched, and their coordinates and their class are automatically labeled. So you can potentially get an unlimited number of new images. So how it works, maybe you know the pollens have different sizes. Some are giants compared to others. So the recompositron draws pollens to scale, and so all sizes are proportional to the real size. Another feature is to offer a gallery of backgrounds. And finally, the software allows to generate noise on the images. Thanks to this process, we were able to build a dataset of 10,000 labeled images to start. So we were able to train the different models. We used TensorFlow Object Detection API to make it, with a Jupyter notebook based on Azure machine learning to benefit from the computing power of Microsoft, you know. We made different experiments with some state-of-the-art models, like faster RCNN, YOLO v4, YOLO v5, efficient date. We had to evaluate what is the best algorithm to detect pollens. And from these experiments, faster RCNN was the best one. You can see the results on the next slide. We have a map around 93%. It's a very good precision. MAP means mean average precision. This is the most important metric to evaluate an object detection model. And you can see the bounding boxes around the pollens. It's the detection. And inside these boxes, the algorithm makes the pollen classification. So as you can see, it's good, and the occlusion is good too. So we're proud of it, really. It's a good job, I think. The next slide is for you, GP.
Yes, but just to summarize that part. So yes, it's a very difficult job for data scientists to predict that we are able to predict something. So it's something iterative. So we haven't the conviction at first that we don't have enough data. So after the first batch, we have seen that there's not enough data, so that's why we decided to create the data just to go on. And like Jonathan says, we optimize, we parameterize. It takes a few weeks to do that, to have the right algorithm with good prediction and something realistic. And we are very happy about that because it's like a deep fake. We have trained an algorithm with fake images. And the first time, I don't know if you remember that, Kim, we show the generated picture. So it wasn't a real microscope lamella, but it was a generated image. There's a kind of wow effect. Oh, where have you got that images? Do you know some bees or some laboratory technician? So there's a wow effect. There's a kind of deep fake, but it's not as precise as a real image coming from a real microscope with real pollen inside. So some laboratory technicians just point out some pitfalls, some flaws in our algorithm. Just because, for example, we discussed with a university, and they said, "Oh, it's impossible to have that pollen and that pollen in the same image," just because the first one is in France and the other one is in Africa. So there's some flaws in our algorithm generation. So, but it was the first step to make the discussion and to go one step further and to enhance the algorithm, just to know what is how a laboratory technician see the pictures and how he works every day. And the things we need to implement into the algorithm is to take in consideration what we call the stacking. So the idea is a laboratory technician just move the lamellas under the microscope and just to simulate a kind of 3D of the pollens, because it's not just 2D, it's not an image, it's something that is on a glass with a microscope. So we need to the next step of the project, because we have good results on 2D images, but the next step is to implement that kind of stacking. So to consider that we need to take few images to retrace, to rebuild the 3D, the pollen in 3D, because it's a sphere. It's not just it's not just a circle. Kim, do you confirm that you had the wow effect when we first show you that kind of images?
Yes, I confirm. I think it was very great. And the other way, I confirm also that the stacking, it's the real issue for the next step.
Yeah.
That it's true that we are working in 3 dimension when we are using the microscope, and actually the image is in two dimension.
Yes, yes. So it's something we need to implement. And why I explain that part, it's just because artificial intelligence, and it's even the case in the green field, in the biodiversity field, you need to have something, a kind of iteration, because it's very difficult for people like Kim that are an expert on biodiversity, on bees, on plants, on flora, and to understand what people like Jonathan and me are explaining around artificial intelligence. So it's very that first version of the algorithm was very important to explain to scientists like Kim, but we had the same discussion with different universities in France, working with Pollens. It can be for biodiversity, but it can be for palynology, sorry. So they studies the pollens, but in the past, just to see the impact on the climate from different period of the history, or maybe the allergology. So you know that a lot of people are allergic, have some allergies with the pollen. So that kind of algorithm is very interesting for a lot of people that every day counting and classifying pollens under a microscope. And that these discussions are very important to improve, because we learn from them, because they know how to identify the pollens. And us, Jonathan and me, we know how to implement something, a kind of black box magic that can take the image and say, oh, I have seen that taxon, that pollen, that pollen, that pollen, that pollen. So it's very passionating to discuss with people like him, and to help him to improve his job and the impact he have on that. So just to conclude and to finish, and I think we are on time. The idea is we wanted to, because it's for everybody, and the idea behind ShareAI and the Microsoft France initiative is to have something that is not just for few people, but that can help, that have impact on the society. So we have decided with Kim and Microsoft to put that project in open innovation. So the idea is to put the data, to put the algorithm, to put also the result on something that is public. It's not all open. It's on GitHub, and you need to request access to put data or to use the data, because Jonathan didn't mention, but we did a very not complex but boring job to take public databases of pollen and to make the transparency around each pollen. So there's a lot of work to have something clean and usable for anybody. So it's on GitHub. Just send us an email, and if you want to improve the algorithm, working on stacking, for example, if you want to share your data, if you want to use the data to make your own algorithm, it's the purpose of that project. And regarding the biodiversity result, it's only for stakeholders and people involved in the project. Do you want to add something, Kim, about the project, the needs, and everything?
No, for me, it's very nice, and it could be very interesting if you can obtain some picture from everywhere, because I think it's really also one of the big issues is to have enough picture from everywhere, because it's not maybe only in Belgium, in France, or in UK, but maybe in US or in Africa. Because this topic, we discuss about allergies or the topics, but I think we can also discuss about invasive plant species, and we need also to have all of the picture about this kind of pollen to help the people also to act to preserve the biodiversity and the environment. Thank you.
Yes, great. Pollens and biodiversity, it's something that is worldwide, not just Europe or UK or France or wherever. It's worldwide. So thank you, Kim. And the idea is to let some time for discussion. So I don't know if there was some interesting questions or remarks on the chat, James.
Yeah, we have had a few questions actually. I might kick off. So there's one I think which does relate to one of the ones that comes through. So I mean, firstly, what you've done is absolutely amazing and super fascinating. It's insane actually what you've been able to achieve. I'm curious about some of the kind of like broader applications of this, kind of like beyond this kind of specific use case. Are there like, where do you think this kind of like technology can kind of go in the future, like beyond this kind of specific example?
Maybe you want to answer if you have an idea, Kim, first, or I can.
Not really, because I think it's more about the technique, but I think for me, and I think we can use that just for the pollen, but maybe it can be very useful just to recognize the plant in the environment in the future, you know. Maybe we can use the same technology if we have enough picture to take a picture of your garden and to identify all the plants of your garden, you know, and not maybe just with the pollen. It could be very useful, I think. And I use also not the technology, but the pollen to identify the plant species in natural area in the US, just because some of our partners ask us to identify that. And I think we can really identify many samples everywhere in the world more efficiently than what we are doing now, because it's very hard to have the specialists to identify all the pollen from all the countries actually. That's the same for the plants.
And I can add something. You are working on that kind of project because recognize, classify the plants in everybody's garden, and just because the final purpose for you is to get biodiversity data, because with biodiversity data you can suggest, you can propose actions to enhance or to preserve the biodiversity. And as a technologist, I often say to customers or partners that we can do almost everything with artificial intelligence. It just, do I have enough data and enough parameters to tell the algorithm how to classify or how to identify? So everything is not possible, because you know that a lot of people working on it, but the base of the computer vision, it's the same. We need to have some labeled images to tell, oh, look at, if it's round with I don't know, a yellow border and maybe some little peaks on that, you can say that it's a pollen of blah blah blah. So we train, it's called machine learning. So we just explain the computer how to do that. It's not so easy, but at the base we can do that for everything. So the idea to do that with the plants, I know that a lot of people try to have the magic algorithm that can identify any plant in the world. There's also people that do implement that for birds. I use it last weekend. But what is difficult is to have something that it's not too specific. It's easier with a microscope image, just because somebody has prepared the thing we have to identify. In your garden, you have the light. Maybe you have some shadow with trees. Maybe the people is not good to take the picture, so maybe the picture is have a kind of blur. So it's difficult to have every kind of images and every kind of garden that exists. But a lot of people work about that, and we know that the tech can help to do that, and in few months or few years, it won't be an issue.
You're right. That's amazing. It's impressive. There's a question from Noor, which says, can you do also a forecast of pollen? Could it help countries' borders numbers to check against weeds or alien species?
Honestly, we can do it with a microscope actually. Then that could be useful, really.
Okay.
But most of the time for the invasive species, it's not just for the pollen. It's just because you know, in a big container that coming from one country, sometimes you receive some samples and we can identify the plant inside. You know, very close to the banana, we can have an insect, and it's an invasive insect, but we can have also some invasive plant. We don't need the pollen identification for that, in fact. But what we are doing about the invasive plants is just when bees are working in a radius of 1.5 kilometers, you know, and sometimes we can check for the potential emergence of new invasive plant species. With the collection of pollen by the bees, we can say at one moment, okay, because it's not only it's not 1 year, it's months per month, we can say, oh, it's just new, but this month we identify an invasive plant species. Then we can work directly with the stakeholders in the fields to remove it. and just in the good area, then it's in this context that we are working with the pollen for the invasive plant species.
Yes, and at first it was one of the main idea to have a kind of big data of the biodiversity of a place, of Europe or France, and you ask us to extrapolate the data, so to make a kind of forecast of data, just to have a map of all the biodiversity in France or in Belgium or in Europe. But it's difficult to invent the pollen. The best way is to collect with the bees.
Yeah. And so another question from the audience. So this is from Suresh. What technique did you use to count the number of pollen in an image? So how did you actually count this pollen?
It's my part, I think. Well, the AI model just makes the detection. The counting part is the part of the software that arrives before the detection and the AI model work. We made it with a Flask and a Python function. That was very simple compared to the AI training. Well,
yes, it's something that it's sometimes difficult because we expect that the algorithm make everything, but in AI sometimes the AI part just make a prediction that is used by a broader solution. So here the idea, and it's not implemented because it was just discussion with I think it was with University of Montpellier. It just if you can command and control the microscope, you just say the microscope to take pictures, and you move the microscope to have a map of the lamella, and then once you have identified, you just count the bounding box. So, for example, if you have 100 pollens on the big pictures, not just one pictures, but the whole picture of the lamella, you just say, oh, I have seen 3 of that, 5 of that, but it's not the artificial intelligence algorithm that do that. It's just a developer work to use the work of Jonathan and to say, okay, I will give it the 5x5 images and to recompose the result and make the score.
Yes,
it's almost that. So that's why we need some developers, traditional developers. Here the data scientists work with Python, but it can be done with any language or any solution.
Mm-hmm.
Okay, interesting. So what about, why is it so difficult to count pollens in the first place? What makes it such a kind of challenging exercise?
Do you want to answer, John? I think the answer can be on different parts. The difficulty for the computer, there's no difficulty except the training. So the difficult part is to train and to validate that it's good. But basically, it's difficult just because it's a long process. There's a lot of the technician laboratory do a lot of operation in order to count and to identify the pollen. So we accelerate the end of the process, but there's a lot of operation. For example, you need to do some operation to put the pollens under the microscope. So it's the first thing, and there's a lot of manipulation, and for some pollens you need to use some I see Kim correct me if I'm wrong, but you need to have some chemical manipulation of the pollen. So it's very difficult because it's not so easy that you take the pollens in your hand and you say, oh, there's a lot of this or a small part of that. Do you want to add something, Kim, about the complexity of the counting and identification of the pollen?
Yeah, it's true that for the counting, the preparation it's very important, because when the bees are coming back with the pollen, it's not just one grain, it's a pellet of pollen. That means you have a lot of pollen into a small pellet. And when we will analyze under a microscope, we need really to mix all the pollen together, because we really risk to only analyze one kind of pellet and not the real the mix of all of this pollen, because that can come from many different kind of plant. And if I only put one pellet, I will analyze one kind of plant. And I can say I have 100% of this plant, but it's just because I didn't prepare correctly the samples, and finally I don't analyze all the pollen into the samples.
And at first we were ambitious because we wanted to do that directly in the hive. And I know there's some people in my team that were that want to develop something mechanical to explode the pellet, but it was too difficult. It's a specialist job, and it should be it should be done inside the laboratory.
And if I can add also that we had also some chemical preparation, because like this, the pollen is more transparent, and as it is most transparent, we can really look at in 3D all the parts of the pollen when it's under the microscopes. And we are moving really to see all the part of the pollen, because we need, when we identify the pollen, to identify all the holes, because there are a lot of holes all around, and we are supposed to count them. That's why when you are only in 2 dimensions, you cannot see the holes under. It's just an example for the holes, but you cannot count all the holes on the pollen. That's why I think the 3 dimension probably will be the best way to identify the pollen.
Yes, and there are solutions, but I know that there are some Chinese patents about other techniques of classification of pollens, but the issue is that the whole solution is too expensive, and it's not affordable for people that just want to help for the biodiversity. It's
Got it. Interesting. I'm conscious of time. If there's any more questions from the audience, then feel free to drop them in. There's a couple more for me, I think. So obviously you're like heavily, like the algorithm is obviously key to the work you've been doing. Is there anything missing from your algorithm at the moment? Like what's the missing piece there?
John, do you want to answer?
Sorry,
I have a word.
My connection is very bad. Sorry.
Oh, so
what's the question?
Every data scientist will tell you that what is missing, data. The more data we have, the more precise and the less bias there are inside the detection and the algorithm. So
yes.
we need to have data. We need to have real world data. So sometimes people just say, oh, we will prepare that for you. No, just give us what you see on your microscope, and we will tell you. We will train, test, evaluate, and then we say, oh, there's bias with that. We need to balance the data, and then we ask for more data. But the more data we have, and that's why the idea about open innovation, it's to tell every university to share their data, to share their microscope pictures. But I think it's very difficult because, for example, a lot of universities that we are discussing with don't know about GitHub and open innovation. They are used to work with their colleagues around the world. They are not just in their universities, but they don't know about artificial intelligence. They don't know. For them, we are just like aliens, where it's or magicians. And the idea behind speaking about that project is to say, if you work with pollens and you have some images, give us, we will retrain the algorithm, and you can benefit from that algorithm. So it's the idea, give data, we can improve it, and we give you back the algorithm.
All right. Data is key. It's all about the data. Okay, so final question, I think. What are the next steps for your kind of opportunity? So where to from here?
Currently, we are in standby because we need to remove the bias of the deepfake pollen images. So we need real world data just to have something that is confident enough or accurate enough for the industry. The industry is it's the science. So it's the next step, the direct next step, and we are very excited to try to implement stacking, because it's a challenge. It's not just a matter of having more and more data. We need to adapt the way. So Jonathan just shared about faster RCNN, TensorFlow, but we need to have a different approach to have that kind of 3D, the stacking. And another next step, and it's for me, it's more my part. I am less data scientist than Jonathan. Is to have something to, for example, having a microscope and try to implement the automation of the microscope. So I'm not specialist in microscope, but I know that some microscope have API, so we can command and control the microscope. And my part, it's IoT, and here it's an IoT project, just to have a connected microscope to make all the automation, and the laboratory technician just put the lamella under the microscope, and on the outside, on his mobile phone or whatever, he just have the score. So having more real-world examples, implement stacking, because we know that it's a real bias that we have, and then automate, connect a microscope and automate the image collection.
Got it. Awesome. Thank you so much. So thank you, Jean-Pierre. Thank you, Jonathan. Thank you, Kim.
Thank you.
That was really, really interesting and really great to hear from everyone. That is a wrap there. So I would encourage everyone, if you haven't checked in already, you can do so, and then there'll be some kind of, you can get access to documents. This is part of a series. So next week, at the same time, the same place, we have a bit more of a kind of hands-on training session around kind of using software for sustainability, but all under this kind of green tech series that we're running at the moment. So please do check that out. You can see the link to kind of see the full series there. We've also had some other sessions in this series, which you can actually view on demand if you go to that link as well. So again, thank you to our guests today. That's been awesome, and thank you everyone for joining in the chat.
And do you want just a fun fact, James? The project that will be presented next week, we know it very well because Jonathan worked on it a few years ago when he was an alumni of the Microsoft AI school in Paris. So we have Jonathan have worked on that project. So it's a very fun fact to have that episode next week.
Obviously, that was completely planned, and that's why we've got that happening. So, no, that's fantastic. That's cool. Okay, thank you ever so much. Thank you everyone for joining.
Thank you.
See you next week. Cool.